Yeah. So can I start now, sir?
Yes.
Okay. A very good evening to everyone. Sorry for the delay. I was having some technical issues. Fine. So let's now get started into the session. So today we are going to discuss on aerodynamics part, previous year solutions for this 2013 GATE paper. Okay. So let's see how was the mark distribution and how many questions were asked in this year. So as you can see here, there were 3 questions of 1 mark. There were 6 questions of 2 marks, and in total, aerodynamics part was for 15 marks in GATE 2013. Okay, so let's now get started and look into each of these questions, how to solve them, right? So here you can see the first question. This was question number 10 in 2013 paper. So it's 1 mark MCQ. Okay, so let's read. The x and y velocity components of a two-dimensional flow field are given to you. So you're being given with the velocity components, which are u and v, right? Where c is a constant. The streamlines are a family of what? So this question is asking about the type of streamlines that you can expect in such a flow with these velocity components, right? So to solve this question, let's first understand a little bit about the concept of streamlines, right? So I'm sure you guys would have definitely learned about streamlines, which is something we most commonly use, widely use to analyze flows, right, in fluid dynamics. So you would have learned this in fluid kinematics, but let me still revise streamlines for you. So what are streamlines? You know, streamlines are lines which are tangential to the velocity vector, right? Lines which are tangential to the velocity vector in a flow field, right? And you know very well that streamline is essentially a 2D concept, right? It's a 2D concept. So you cannot define streamline for per se a 3D flow field, right? I mean, you have 3D flow field, but these are lines which can be visualized only in a 2D plane. So you can have flow which has components in all 3 directions. You can have the x, y, and z components of velocity, but still when you speak about streamlines of such a flow, you will be visualizing them only in 2 coordinates. I mean, in a plane, right? So this is essentially a 2D concept. Okay, so it is only for a 2D flow. So now let's see what is the mathematical equation that governs the streamline. So for example, I give you the velocity components for a flow. Let's say v, which is u I cap plus v j cap plus w k cap. Okay, so if I give you such a velocity components or a velocity field for a flow, how do you find out streamlines, right? You know, let's assume there is a streamline. Okay, let's consider this is a streamline of a flow, a certain flow, and you identify a fluid particle on this streamline. So let's say this is the fluid particle. Now this fluid particle moves with a velocity v. Okay, v. And if I want to, if I just tag this particle in the streamline, and if I draw the position vector of the streamline at the point where this fluid particle is present, right? So let's say that particular position vector is given by ds. Okay, ds is the position vector of that streamline, right? Or the particle which is moving through the streamline, right? So now you can see by the definition of streamline that it is the line which is tangential to the velocity vector. So if it is tangential, then how can I represent it? I can say v cross ds will be equal to 0, right? The cross product of velocity vector and the directed position vector is going to be 0 because they are essentially in the same direction, right? So under this condition that v cross ds is equal to 0, under this condition, uh, what can you, I mean, how can you represent this condition? This can be further, you can expand this, right? So you can solve using this matrix, right? So you write down the velocity components over here, right? This is I, J, K. Here you write down the velocity components and here the position vector, right? So this is how you solve for this cross product, right? When you equate it to 0, you obtain the equation of streamline. So what is the equation that you obtain, guys? What is the equation that you obtain? You obtain dx by u. So this is essentially dx, dy, dz, right? So dx by u is equal to dy by v is equal to dz by w. So this is the equation of a streamline. Okay, this is the equation of a streamline. So let's use this equation now to solve the question that we have, right? So for us, they have given the velocity components already. So what are the velocity components? U is equal to cy by x square plus y square. V is equal to cx by x square plus y square, right? These are the velocity components that is given to you. Now, so this is an xy plane, right? They've told it is a two-dimensional flow field, which is an xy plane. So the equation of streamline for this would be dy by dx is equal to v by u. Okay, where v is the y component of velocity and u is the x component. So you take the so you take v by u, right? You see the denominator is same and c is the constant which is same in both the components. So what you get x by y, okay, x by y. So now I can say this is y dy is equal to x dx, right? So this is sort of a differential equation. You can now integrate, okay, integrate between any two points. This becomes y squared by 2 is equal to x squared by 2 plus some constant, right? Or I can say x square minus y square is equal to some other constant k, right? So this is the general solution for this particular uh, differential equation, right? X square minus y square is equal to k. Now you look at the options and figure out this particular solution corresponds to which curve, right? So this corresponds to hyperbola, right? You know the general equation for an hyperbola is x square by a square minus y square by b square is equal to 1, right? So this equation resembles the equations of hyperbola. So the streamlines are nothing but hyperbolas. Okay. So whenever there is a question on streamline, just see the velocity components and use the equation of a streamline to uh, find out what is the sort of curve that the streamline represents. Okay. I hope this question is clear to you all. It was very easy. Is it clear to everyone? Okay, let's now move on to the next question. Right. So there's the next question. You see here, consider a thin flat plate airfoil at a small angle alpha. Okay, at small angle alpha, this is important that they have told the angle of attack is small, right? To an oncoming supersonic stream of air, right? So you have an airfoil that is placed in a supersonic stream of air. So essentially, the Mach number of free stream is now greater than 1. Assuming the flow to be inviscid, CD by CL square is going to be what? So they're asking you this thing, CD by CL square, whether it is a function of your angle of attack or not. Okay, so this is what we have to find out in this question, right? So let's try to understand about something about the supersonic airfoils. So there was a similar question in I think gate 2011, and we had solved that in one of the sessions. So if you guys have any doubts on what is a supersonic airfoil and what is the theory behind it, please go and look at that session. So I had explained about the shock expansion theory, right? So essentially, supersonic airfoil, supersonic airfoils are not the conventional subsonic airfoils that we use in aircraft, right? So these are generally like biconvex airfoils. Okay, these are biconvex airfoils. Now, what is a biconvex airfoil? Biconvex airfoil is something like it has, I told you, it has a blunt leading edge, and you can see it has a sharp sort of trailing edge. Okay, so it's actually a derivative of the diamond shaped airfoil, right? So you have the diamond shaped airfoil. Okay, so this biconvex airfoil is sort of the derivative of that, right? Now, why do we use this diamond shaped airfoil in a supersonic flow, right? Because when you have a supersonic flow, which is m greater than 1, and you have a diamond shaped airfoil, you see that there are corners, right? So what will happen, guys, when you encounter a corner, a compression corner in a supersonic flow, you're going to have a shock, right? You're going to have a oblique shock. So here you're going to have oblique shocks, and then so the flow is going to turn over here, right? And then you encounter another corner, which is an expansion corner, right? Because this corner will deflect the flow away from it. So you're going to have expansion fans over here. Again, here you will have an oblique shock, right? So the entire flow dynamics around this supersonic airfoil is governed by shock expansion theory. Okay, shock expansion theory, which you must have studied in your gas dynamics, right? All right, but that was just about supersonic airfoils. But what does this question ask? I'm sorry. When you have a supersonic flow and a supersonic airfoil, biconvex or a diamond-shaped airfoil kept in such a flow, you're going to encounter obviously lift and drag because of the shock expansion, right? Because of the pressure differences, which is generally due to the shocks and expansion waves. Now, if you place this airfoil at an angle of attack, say alpha, right? If you place it at an angle of attack of alpha, then we know from from linearized supersonic theory. Okay, linearized supersonic theory. So what is this linearized supersonic theory? So it is, as we have the potential flow theory for a subsonic incompressible flow. Similarly, you can also develop a potential flow theory for a supersonic flow, right? But when you want to develop it for a supersonic flow, you should remember that the compressibility effects is going to come into picture, right? So it's generally called a small perturbation theory. Okay, so you take into account all the perturbations in the supersonic flow, and then you linearize those equations, right? When you linearize them with some assumptions, you getting there was a pause due to some network interruptions. So I'll start again. So we are discussing this question on thin flat plate airfoil, which is kept at supersonic flow, right? So we were discussing about the supersonic airfoil. So I told you we use generally biconvex airfoils or diamond-shaped airfoils for supersonic flow. And the aerodynamic coefficients here are functions of alpha and Mach number. Okay, so you can see here CL and CD as they are given by these formulas. These are directly from the linearized supersonic theory. If you want to know more about this, please refer the section in John D. Anderson. Okay, so this is the formula for CL and CD. Now, what is asked to us is CD by CL square. So when you find CD by CL square, what do you obtain? CD is 4 alpha square by root m square minus 1. CL square nothing but 4 alpha by root m square minus 1 the whole square, right? So guys, when you do this, when you do CD by CL square, what will you get? Can you now tell me the answer for this question, guys? If you are watching the session, what will you get? What should be the answer? Is it dependent on alpha? Is this ratio dependent on alpha? Yeah. Yeah, this ratio is not dependent on alpha. So you can see that the alpha square and alpha square terms get simply cancelled out from the numerator and denominator. Yeah, Ashish, you are right. So it is going to be independent of alpha, right? And this we already know that the drag, right? The drag is directly proportional to the drag coefficient is directly proportional to CL square, right? We generally write CD as CD naught plus KCL square, right? This is what we write, the drag polar equation. So, CD is already proportional to CL square. So it is only related through some constant, right? So it is not going to be dependent on alpha. All right. Yeah, all those who have commented, the answer is B. You are absolutely correct, right? So that's what we have seen now. Let's now move on to the next question. Okay. So this is a very easy question. So this question says critical Mach number for a flat plate of zero thickness at zero angle of attack is dash. Okay. Now, now this was an NAT. Okay, this was an NAT. So can you guys comment the answer? What should be the answer for this question? What do you think should be the critical Mach number? Yeah. Okay. I think there's some lag in the video. Yeah. Sahil, you are right. So the critical Mach number in this case would be 1. So let's try to understand what is this concept of critical Mach number and why in this case it is 1. In general, when you see the critical Mach number for an airfoil, for a subsonic airfoil, it is usually around zero point 0.7 to 0.85. Okay, so the conventional aircrafts, the civil aircrafts that fly, they usually fly in this but in this regime of Mach number, that is due to the effects of critical Mach number, right? Let's see what is this critical Mach number. So critical Mach number, MCR, okay, it is a Mach number. It is actually the free stream Mach number. Okay, it is the free stream Mach number at which a supersonic at which a sonic flow, okay, sonic flow is when m is equal to 1, is first encountered on an airfoil. Okay, so when you have an aerofoil, okay, let's say there's an aerofoil, and if I keep it in a supersonic flow, okay, sorry, if I keep it in a subsonic flow, okay, if I keep it in a flow, let's say where the Mach number is of the order of around 0.8, 0.85. So if I keep it in such a flow, uh, what will happen, guys? The flow is going to accelerate on the upper surface of the aerofoil, right? Where the pressure is going to decrease. So the flow is going to accelerate. And as a consequence of this acceleration, the flow, the velocity is going to increase, right? The Mach number is going to increase. When the Mach number increases, you will find that for a given value of free stream Mach number, okay, for a given value of free stream Mach number, at some point on the aerofoil, okay, at some point on the aerofoil, you will find that this is m infinity, is a free stream Mach number. You will find at some point the Mach number is going to be equal to 1, right? So that particular free stream Mach number at which you first obtain a m is equal to 1, that is a sonic flow on any point on the airfoil, is known as the critical Mach number. Okay, that is the critical Mach number. So this is usually, I told you, it's going to be around 0.7 to 0.85, right? It depends on airfoil and the free stream conditions. Okay. It also depends upon the altitude at which the aircraft is flying, right? So all those conditions apply over here. So that is the definition of critical Mach number, right? So essentially the flow will try to expand and the Mach number will increase. At a point you will find the sonic flow, right? That free stream Mach number becomes your critical Mach. Now what is given to you in the question, please observe carefully. They have told that you have a flat plate of zero thickness at zero angle of attack. So essentially, I am just having a flat plate, okay, of zero thickness at zero angle of attack, and I simply have a flow, okay, some flow of say your Mach number is m infinity. Now, what is going to happen, guys? Can you tell me if there is going to be any expansion over the flat plate? Can you expect any expansion over the flat plate? Will you have an expansion? Will the flow expand? Is the Mach number further going to increase? See, there is no thickness for the flat plate and it is also kept at zero angle of attack, right? There is no curvature of streamlines at all. You know, the flow over a flat plate is a zero pressure gradient flow, right? With absolutely no curvature of streamlines. So you find that there is going to be no expansion of flow at all. So whatever is the Mach number, the free stream Mach number, that free stream flow is going to be simply convected on the flat plate with the same velocity, right? With the same velocity. Okay. And here we are not even considering the viscous effects. Otherwise, there is going to be a, there is going to be boundary layer, right? But that is only if you consider the viscous effects. Let's assume the flow is inviscid. Okay. So when the flow is inviscid, you are not going to have the boundary layer effects. So essentially, whatever is the Mach number, the free stream Mach number, the same Mach number is what you will find at all the points on the flat plate. Now, to obtain critical Mach number, I need to get Mach number equal to 1 on the flat plate, right? When will that happen? That will only happen when your free stream Mach number is equal to 1, right? Obviously, because if your free stream Mach number is not 1, you are never going to get Mach 1 on your flat plate because there is no expansion of the flow, right? So your free stream Mach number must be equal to 1 to get a Mach number equal to 1 on the flat plate, right? So what should be your critical Mach number, guys? In this case, it should be equal to 1, right? So this follows from the definition of critical Mach number. So I hope this is clear to you all, right? There is no doubts. Let's now move on to the next question. Okay, this question is actually from compressible flows from gas dynamics, but nevertheless we can solve it, right? Let's see what is this question. Consider one-dimensional isentropic flow, okay, one-dimensional isentropic flow at a Mach number of 0.5. Okay, so what is the free stream Mach number? Mach number is equal to 0.5. If the area of cross section of stream tube, okay, stream tube is nothing but it is a collection of streamlines. Okay, it's a collection of streamlines that form a closed contour. Okay, that becomes a stream tube. You can also visualize stream tube as a duct, as a duct, as a pipe or a duct. Okay, if the area, cross sectional area of that duct increases by 3% somewhere along the flow, the corresponding percentage change in density is dash. So obviously you see that the Mach number is 0.5, right? Which is well above the incompressibility limit, right? So it's above 0.3, which means the flow is going to be compressible. Whenever you have a compressible flow, you know there is going to be density involved in your equations, right? Now they have told that the area somewhere increases. So what happens to the density? So guys, can you tell me which is the equation that relates your density, area, Mach number, which is that basic equation for your 1D compressible flow. Yeah, for 1D compressible flow, which is that basic equation that relates your density, area, and velocity, because Mach number can be written in terms of velocity, right? Which is that equation? That is the continuity equation, right? That is simply the mass conservation, which we all know, right? So let's see what is the mass conservation equation. You know, rho into A into V is equal to constant, right? According to mass conservation. Remember, this is for a 1D flow, right? It is for a 1D flow. When you are writing it for two-dimensional, three-dimensional flows, then you have to express it in either the differential form or the integral form, right? So this is valid only for 1D flow. Okay. So rho AV is going to be equal to constant. Now, if I differentiate this, so I can say d of rho AV will be equal to 0, right? So if I just expand this, I can say AV times d rho plus A rho times dV plus rho V times dA equal to 0, right? I'm just applying the chain rule of differentiation. Okay, this is what I get. Now, if I reverse complete equation by rho AV on both the sides, what will I get, guys? I will get d rho by rho plus dA by A plus dV by V is equal to 0, right? So this is one of the intermittent forms of the continuity equation. Okay, this is one of the intermediate forms of the continuity equation for 1D compressible flows, right? So let's use this particular form of the equation to solve this problem, right? Now they have given you the area of the cross section increases by 3%, right? So the dA by A, change in area by area, is given in percentage, right? And they have asked you what happens to a change in density, right? And you know that is also related to the change in, sorry, not volume, change in velocity. So we have to now express, because the Mach number is given to us, we have to now express these quantities rho A in terms of V, right? So that we already know there is a relation called as area velocity relation. Okay? Area velocity relation for flow through ducts. Okay, you have area velocity relation for flow through ducts. So what is that area velocity relation, guys? That is dA by A is equal to 1 minus m square times dV by V, right? So you know here by this equation that if your flow is going to be subsonic, right? That is, say if you have a duct like this, and if you have a subsonic flow, which where your m is less than 1, then you know that area and velocity are going to be in, they're going to be oppositely related, right? For example, when your area increases, your velocity is going to decrease, and vice versa, right? So this is the equation that governs your area and velocity for a compressible flow, right? For an incompressible flow, we already know that is A into V is constant, right? But this is for the compressible flow. All right. Now they have already given you M, right? The M is given as 0.5. Mach number is 0.5. So what is your dA by A now? dA by A is equal to 1 minus 0.5 square times dV by V. Okay. So this becomes dV by V becomes dA by A times dA by A times 1 by 0.75, right? Now let's use this particular relation that we have derived now in this equation. Okay, let's call this as equation number 1. Let's use it in this relation. So d rho by rho plus dA by A plus dV by V, that is nothing but dA by A times dA by A times 1 by 0.75, right? I think there's a negative sign over here, right? There is going to be a negative sign over here. I think somewhere we are missing a negative sign. So please check. Yeah, there is a negative sign here, right? In the formula itself. So this is going to be negative is equal to 0. Okay. So from here, you can now write d rho by rho plus dA by A into 1 minus 1 by 0.75 is equal to 0. Okay. And dA by A is the percentage change in area has already been given to you as 3%, right? Which is 0.03. So when you solve this, when you solve for d rho by rho, what you will obtain is that d rho by rho is equal to 0.01, or I can say percentage change in density is equal to 1%. Okay. So what is the percentage change in density, guys? It is going to be 1%. So you see this, it was an NAT, so your answer should be 1. Okay. They've asked you the percentage change in density. Although this was a question of compressible flows, I hope it was a good revision for you guys, right? This is fairly straightforward. You just had to apply continuity equation. Let's now move on and see the next question. Yeah. So this is the next question. So let's read. The potential flow model for a storm. Okay, you have a storm which is represented by the superposition of a sink and vortex. So it is a superposition of sink and vortex, where the stream function can be written like this, right? So it is a addition of the stream function of sink and the vortex. Assume a constant air density, so it's an incompressible flow. What they are asking you is the gauge pressure at a distance of 100 meter from the storm eye, right? So let's see how do we approach this question. So you have a storm, right? So it's like this. Okay, you have it's a combination of sink and vortex, right? The combination of sink and vortex. Okay, so your psi is minus lambda by 2 pi theta plus gamma by 2 pi ln r. Okay, which is the sum of the string functions of sink and the vortex. So you have to find out pressure at a point, right? So you know the equation that relates pressure and velocity in an incompressible flow is obviously the Bernoulli's equation, right? So we have to apply Bernoulli's equation. But to find pressure, you need what? What do you need, guys? You need velocity, right? So how will you find velocity from stream function? You will find from the differentiation, right? So let's find the velocities. What is VR? VR is going to be 1 by r dou psi by dou theta, right? So it is minus lambda by 2 pi r. Similarly, what is V theta, guys? V theta is minus dou psi by dou r, which is going to be minus gamma by 2 pi r. So these are the velocity components, right? Now you are given that lambda and gamma are equal to 100 meter square per second. Okay, and you have to find out the velocity at r is equal to 100 meters. So what is the velocity at a point, guys? Velocity at the point is going to be the resultant of these components of velocity, which is square root of Vr square plus V theta square. So if you just substitute, it's going to be 100 by 2 pi 100 square plus again 100 by 2 pi 100 square. Okay. So what is this going to be? This is going to be 1 by 4 pi square plus 1 by 4 pi square, right? Which is 2 by 4 pi square, right? So this is like 1 by root 2 times pi. Okay. I hope this is clear to you. So this is the velocity at the point where r is equal to 100 meter. So r is measured from the center, from the axis of the storm to the distance where the radial location is 100 meters, right? Now you have to find out the pressure at the point. So let's use the Bernoulli's equation, right? So what is the Bernoulli's equation, guys? P1 plus half rho V1 square is equal to P2 plus half rho V2 square, right? Now, because they are asking you to find out the gauge pressure, okay? Because they're asking you to find out the gauge pressure, we are here neglecting the gravity terms. So you also have the elevation head, right? Plus GH terms. So we are neglecting that because the point at which you want to find out the pressure is at the same height. Okay. So let's assume 2 points. The first point is at r equal to 100 meters from the storm I, and let the second point be an arbitrary point. Okay, you can choose the point wherever you want. So let's choose that point to be at infinity. Okay, so let that second point be where your r is infinity. Why am I choosing it to be infinity, guys? Because you see, when your r becomes infinity, your velocity is going to be zero, right? The velocity components go to zero, right? So that in essence, it becomes a stagnation point. So for such a flow, stagnation point is at r is at infinity, right? So in that condition, your P naught is going to be P plus half rho V square, right? Now, because that point at infinity, you can assume it to be at the same at the same height, okay, so that uh, there is no effect of hydrostatic pressure distribution, okay, because when you go with the depth, you see that the weight of air column increases and the hydrostatic pressure distribution comes into picture, right? So you can always assume a point where there is no hydrostatic pressure, okay, it is going to be zero. So you can assume that, say, this P naught is equal to zero, and this P is the gauge pressure that you want to find out. Okay, so from here you can see that the gauge pressure is going to be minus half rho V square. So substitute the values. Half rho is given to you as, I think, 1, right? And V square is nothing but yeah, rho is 1.2, V square is 1 by 2 pi square. So it is going to be, you see here, it is going to be minus 1.2 by 4 pi square. So if you see the options, option D is the correct answer. Okay. So you have to be careful here because they are asking you the gauge pressure and not the absolute pressure at the point. All right. So I hope this is clear. Let's move on to the next question. So again, the next question is a very simple one. This is from lifting line theory. Okay. So let's read this. Three identical eagles of wingspan S are flying side by side in a straight line with no gap between their wingtips. Assume a single horseshoe vortex model of equal strength of circulation for each bird. The net downwash experienced by the middle bird is what? So you have to find out the downwash experienced by the middle bird. So essentially you have three birds which are flying side by side such that their wing tips are touching each other, right? So let's draw the scenario and visualize. Okay, you have three birds. Say this is the first bird, this is the second bird, and this is the third bird. Okay, and you know the span of each of these birds is s, right? That is the wingspan. Okay, and when they are flying, it is so you know birds always fly in a formation. So what is the physics behind this formation flying, guys? So you know a lot of if you have watched some air shows and all, lot of aircrafts and even UAVs, they do formation flying. It is because they can minimize the induced drag. Okay, so birds purposely fly in a formation flying so that they can minimize the induced drag. So that concept is being applied here. Let's see how. So you can model this birds as horseshoe vortex system, right? Like just like how our Prandtl had modeled the wing, finite wing, as a horseshoe shaped system. So here you model it like horseshoe shaped vortex. Okay, so here you're going to have, okay, right, and the strength is all gamma. Okay, and you're also going to have some bound vortices, which is say gamma. So you're going to have bound vortices and you're going to have trailing edge vortices, right? All with the same strength gamma. Now, what do you see here, guys? You see that, uh, so say this is bird 1, 2, and 3. You see for bird 2, for the bird 2, you see that the trailing edge vortices of bird 1 and bird 2 are in opposite directions, right? The circulations are in opposite directions. And because of that, they cancel each other, right? So you can completely cancel out this particular circulation. Similarly, you can see here also they are in opposite direction and this also can be cancelled, right? So now I can simply cancel this out, right? So now you see this is just a very simple horseshoe shaped vortex model, and you have to find out what is the induced velocity or the downwash, right? Downwash is essentially the induced velocity at the bird 2. Okay, so how will you find out? You just have to use the formula for vortex, right? When you know when you have a semi-infinite vortex, okay, when you have a semi-infinite vortex line, okay, vortex line, the induced velocity due to this semi-infinite vortex line at a distance r perpendicular to it is going to be minus gamma by 4 pi h. Okay, where h is the perpendicular distance from the vortex line to the point where you are finding the induced velocity, right? So let's so this is minus, but let's take the magnitude, so it's going to be plus. Okay, so here we are trying to find out what is that induced velocity due to the trailing vortices of bird 1 and 3 on the bird 2. Okay, so uh, so let's see. So what is the perpendicular distance, guys, between the bird 2 and the trailing edge vortice of bird 1 and 3? What are these distances? These distances are s plus s by 2, right, which is 3s by 2, right? So downwash at the bird 2 is going to be gamma by 4 pi 3s by 2, and you see both these velocities are in the same direction. So again, they are going to add up, okay, which is nothing but gamma by 3 pi s, okay, which is gamma by 3 pi s. All right. So This is what you can see in the option gamma by 3 pi s, which is option C is the correct answer. Okay. This is very similar to how the horseshoe shaped vortex was modeled by Prandtl's lifting line theory, right? You are using the same concept over here, right? All right. Let's now, I hope this is clear to you all. Is it clear, guys? Okay. Uh, so we have two more questions, but I think it's already time and you have next session also. So what I can do is I can take up two of these questions to the next session. Okay. So I'll explain these questions in the next class, right? Okay. So with this, we can end this session up. I hope there are no more doubts. If you have doubts, please feel free to put in the comment section and I'll answer. Okay. All right. So thank you, everyone.